We've been learning about the relationship between cell potential and the concentration of the species in the cell. And so this is kind of a summary slide. And if you just read through it, it's just a bunch of letters, basically. And there's some things that are a little confusing about it. Q is a lot more important when we're talking about electrochemistry than it was when we were just talking about equilibria. And K is less important. So let's go through this. Under standard conditions, Q equals 1. So Q equals 1, and then the log of 1 is 0, right? And so the cell potential is equal to the standard cell potential. Standard cell potential under standard conditions, right? Standard conditions, 1 molar solutions, 1 atmosphere of pressure for gases. Is that what most cells operate at? Absolutely not. They don't. So it's almost always we have different concentrations than the standard cell potential. And so what we can do is we can look at Q, and Q is easy to calculate. They'll give you the concentrations of the stuff, and you do the products over the reactants, and if there's coefficients, you square it or whatever. You just calculate it. Calculated K so many times, we can do that easy. You calculate Q and you compare it to 1, because 1 is standard conditions. So if Q is less than 1, we're dividing by reactants, remember. Let's write that out. Q is the concentration of the products over the concentration of the reactants. So if Q is larger than 1, we want to talk about less than 1 first. If Q is less than 1, that means the products are smaller and the reactants are larger, right? So if we're talking about equilibrium, is that going to go towards the products or the reactants? It's going to go towards the products, right? Because we've got extra reactants, it's going to go to the products. I know that you meant to say products, okay? It's very confusing. So then we've got higher reactant concentrations. The reaction is going to go to the right towards the products, and the cell potential is going to be larger than the standard cell potential. You follow that, kind of? If Q is greater than 1, that means we have larger product concentrations and lower reactant concentrations. And if we think back to an equilibrium, right? If you increase the products and decrease the reactants, what does the equilibrium do? It shifts away, it shifts back to the reactants. So higher product concentrations, the reaction is going to be driven to the left, and the cell potential will be less than the standard cell potential. Okay? At equilibrium, Q is equal to K. At equilibrium, the reaction doesn't want to do anything. It's like, here, this is where I've been trying to get to. I'm good. And so the cell potential and the standard cell potential are 0, because it's not going to go forward or reverse. Electrons are not going to move. And I think that this is one thing that just kind of cleared up for me as I was looking at this slide before I started talking. In previous chapters, we've done a lot of comparing Q to K, right? And, Q is going to move towards K, and that's, what we're looking at in terms of direction, etc. Here, we're comparing Q to 1, because we're looking at, is the cell potential bigger or smaller than the standard cell potential? We're not really looking at which direction the equilibrium is shifting in. So if Q is equal to K, no reaction is going to happen. And that's what happens when your batteries die. The reactants get used up, it comes to equilibrium, and no more juice, no more electricity. Any questions? Okay. Let's see if we can do this. In an electrochemical cell, Q is equal to 0.001 and K is equal to 0.10. What can you conclude about the cell potential and the standard cell potential? So let's do the cell potential first. So Q is 0.001. What are we comparing Q to? We're comparing it to 1. Because when Q equals 1, the cell potential is equal to the standard cell potential. So Q is less than 1, right? And so does that mean it's going to go more forward or more reverse? Q is products over reactants. When Q is small, that means products are bigger and reactants are smaller, right? So that's going to shift the reaction toward the reactants. So Q is less than 1, so then the cell potential is less than the standard cell potential. And I did that backwards. How did I do that backwards? Let's try that again. So easy to get these things mixed up. Okay, Q is small, so that means the denominator is big and the numerator is small, right? I had it backwards. Okay, so low products, high reactants, that's forward, right? So Q is still less than 1, but then our cell potential is greater than the standard cell potential. Does that tell us whether the cell potential is positive or negative? No, it doesn't. It just tells us whether it's greater than or less than the standard cell potential. So we need to figure out, well, is the standard cell potential positive or negative? We could think about it. Personally, I really like equations. Is it over there? No. And I encourage you to do this on an exam. You know, it's like, okay, relationship between standard cell potential and K. Find an equation on the sheet. Oh, look at this one. Standard cell potential is equal to positive stuff times the log of K. If K is less than 1, then the log of K is less than 0. It's negative. That makes sense? So because K is less than 1, the log of K is less than 0. It's negative. And if the log of K is negative, then the standard cell potential is also negative. And this told us hang on a minute. So E cell is greater than the standard cell potential. But just looking at that, does that necessarily mean that E cell is positive? it could be less negative. So let's see if we can find an equation. Well, that's just going to give us less negative. Apparently I'm missing something. Does anybody see what I'm missing?
So, on slide 17, there is a relationship between E cell and
Oops, 70.
so since the log of the Q is negative and we have negative, I guess the conclusion will be positive.
Yeah, so if Q, the log of Q is negative, then this becomes positive. And so that is going to make this more positive than that, but not necessarily. Oh, I know what I'm missing. I know what I'm missing. That helped, thank you. Where is E cell 0? When Q equals K. Does Q equal K? No. It's still smaller, right? So that's what tells us that the E cell is positive. So here's a question. Do you think I'm going to ask you that on an exam? No way. Absolutely not. Those things are really hard to think about, right? My general feeling about exams is if I'm confused about it, there's no way students are going to understand it, right? So, on one hand, then it feels like maybe a waste of time to even talk about something like this, but if nothing else, you see that I'm human and I don't know everything. Any questions about that? That was just so not awesome. So let's see if we can get back to where we were. So we can construct a voltaic cell in which the two half reactions are actually the same. But it can still generate electricity because a difference in the concentration can drive current to flow. So we can use copper to copper 2 plus, copper 2 plus to copper, the same half reaction, one being oxidized, one being reduced. If we figure out the standard cell potential, it's going to be 0 because one of them's forward and one of them is reverse, right? So calculate the cell potential, it says. And this is where we use the Nernst equation. The cell potential is the standard cell potential minus 0.0592 volts divided by N times the log of Q. Here, we don't even need to go look up a standard cell potential because these half reactions are the same, and therefore this is 0. So this is equal to 0 volts minus 0.0592 volts. What's N? How many electrons are being transferred? 2. How do we figure that out? Well, look at this guy. Started with 0 charge, and now it's positive 2. It lost 2 electrons. This one started with positive 2 and goes to 0. It gained 2 electrons. So N is equal to 2 times the log of Q. And here, Q is the concentration of copper ion on the product side divided by the concentration on the reactant side. So 0.010 divided by 2.0. And so we get 0.068 volts. Forgot to unpause it. Oh well, there's the slide, sorry. So here's a picture of that. Here's the concentration cell with standard conditions. So we've got 1 molar copper ion on both sides. And we attach a voltmeter here, and no current is flowing. Over here, we have 0.01 molar copper ion here and 2 molar copper ion there. There is a difference in concentration. Current is going to flow. The cell potential will not be 0. I wouldn't recommend looking at this and trying to decide, is it going to go forward or reverse? I would look at Q for the overall reaction. Over here, the copper ion is the reactant, and over here, the copper ion is the product. And so our Q is this one divided by that one. So as electrons flow from this side to that side, there's a lot of copper ions here. They're going to get electrons and become copper metal. That's going to reduce this concentration. Over here, when copper gives up 2 electrons, it becomes Cu2+, and that's going to increase this concentration. And this one is going to go until the concentrations are equal. Any questions? So I'm not going to test you on this, but I want to talk about it because I think it makes electrochemistry a little more real. Your body is full of electrochemical reactions. They're going on all the time. Without electrochemistry, you would not be alive. So here is an example of how concentration cells work in your nerve cells. So here we have an illustration of a cell membrane. And there are these pumps that can move potassium ions and sodium ions from one side of the membrane to the other. They can't just go through the membrane themselves. So there are concentration gradients. On the outside of the cell, in the extracellular fluid, the sodium ion concentration is higher, and on the inside, the potassium ion concentration is higher. And this results in an electrical potential across the membrane of about negative 70 millivolts, so 0.07 volts. When the nerve gets stimulated, those channels open and they allow sodium to flow into the cell, And so the potential of the membrane goes from minus 70 up to about 30 millivolts. And other channels are going to open and allow potassium to leave, and then the potential goes back towards its resting potential. So there's this potential due to the difference in concentrations, and then that resolves and the potential goes away. So we get a spike in electrochemical potential at that location in the membrane. That's going to trigger a similar spike further down on the membrane. Oops. So those electrical signals are going to move down the length of the nerve cell. Nerve cells are long, right? And so I was trying to visualize this. It's a little bit like, football fans doing the wave, right? The people to the left, raise their arms, so you raise yours, and then the people, and it goes around, right? That's kind of how these electrical signals are working on the nerve cells. Gets stimulated in one place, and then that signal stimulates next to it, and so it ripples down the cell. When it gets to the end, it's going to trigger the release of a chemical neurotransmitter, such as dopamine or acetylcholine or one of those guys. And that neurotransmitter will go across that synapse, the space between the nerve cells, and trigger the next nerve cell. And then you have another ripple effect of cell potential moving down to the end, trigger the release of the neurotransmitter. And that's how your body sends signals, like, from your finger to your brain that says, hey, you shouldn't be touching your flat iron. And then the brain goes back and tells the muscles, move away, right? And it happens really, really fast. That did not happen yesterday. Well, yeah, it did. Any questions?